Molecular shape is important in determining the polarity of a molecule. We talked about polar bonds. We need to talk about when molecules are polar. So if you have a diatomic molecule where you only have two atoms, there's only the one bond. If the bond is polar, then the whole molecule is polar. But when we have polyatomic molecules, lots of different atoms, you can have polar bonds and still have a nonpolar molecule because those dipole moments from the polar bonds can cancel each other out. So let's look at CO2. So carbon dioxide. We looked at its shape on Monday. It's got a linear shape, and we know that because there are two electron groups on the central atom. So each of these bonds is polar, and we've got the arrow pointing to the more electronegative atom, which is the oxygen. And this one, the arrow is pointing in the opposite direction. So dipole moments from polar bonds are vectors. And at some point in your math education, you learned about vectors. Vectors are like arrows. They have a direction and a magnitude, and so they can be added together. Most people don't retain that information because it doesn't seem useful in everyday life. So if we're looking at something simple like this is really a one-dimensional molecule. Yeah, it's only one dimension, isn't it? It's a line. Vectors are easier to understand. It's a bit like a number line, which, people also have issues with that. But so, if we have 1, 2, 3, and then -1, -2, -3. So this, these two vectors in opposite directions would be like taking -2 and +2 and adding them together. They add up to 0, right? You can also imagine playing tug-of-war, and the two oxygens are playing tug-of-war with each other, and the carbon here is that red flag in the middle. These oxygens are equally strong. They're pulling in opposite directions. Nothing seems to be happening, right? If this oxygen was stronger, then it could pull the carbon and the other oxygen over, but they're equal. And so they're just two opposing forces. Nothing moves. Does that make sense? So we have these two opposite and equal forces, or dipole moments, and so they cancel each other out. So this molecule, even though it has two polar bonds, is nonpolar. There isn't one end that's negative and one end that's positive. You could say, well, the middle is a little positive and both ends are a little negative, but that doesn't do anything because a polar molecule will line up in an electric field. It needs to have one end that's positive and one end that's negative. Any questions yet? Let's look at water. So water, also 3 atoms, 2 polar bonds. But because of the 2 lone pairs on the oxygen, water has a bent shape. It's not linear. And so here we have the oxygen being more electronegative than the hydrogen. So there's, I think of this as like movement. The oxygen is hogging the electrons, and here the oxygen is hogging the electrons. These do not, those don't cancel out because they're not in opposite directions. If you, So if we imagine the oxygen playing tug-of-war, this could be like Dad with his 2 little boys. And so Dad's got his arms out like this, and that kid's pulling that way, and that kid's pulling that way, but Dad's stronger. And so he just backs up, and all 3 of them are moving, right? There's a net dipole moment. So the oxygen end of this molecule is slightly negative, and the hydrogen end is slightly positive. Does that make sense? So to figure out whether a molecule is polar or nonpolar, you first have to draw the Lewis structure and figure out the molecular geometry. So that's what we've just been learning about. Then you have to see, does the molecule have polar bonds? If all the bonds are nonpolar, it doesn't matter what shape the molecule is, there can't be any polarity. If you have polar bonds, then you identify them and draw the little arrows as vectors, and the length of the vector corresponds to the difference in the electronegativity, the extent of the polarity of that bond. And then you have to figure out, do those vectors add up to 0, or do they add up to a net vector? If they add to 0, the molecule's nonpolar. If they don't add to 0, then the molecule's polar. Does that sound a bit involved and confusing? Yeah. Let's look at vector addition just quickly. In one dimension, this isn't too bad. It's like adding numbers on a number line. Positive numbers go in one direction, negative in the other direction. So if we're adding 2, positive 5, so the number indicates the magnitude, and the sign indicates the direction of the vector. So if we take plus 5 and plus 5, that gives us plus 10. If we have minus 5 and plus 10, here the vectors are going in opposite directions, but one is larger than the other. That's going to add to a net vector. It'll be plus 5 in this direction. Minus 5 and plus 5, but in opposite directions. Same magnitude, those will add up to 0. Everybody should be able to understand one-dimensional vector addition. Okay? Gets a little trickier with 2 or more dimensions. I'm going to show you a kind of a shortcut, a hack, where you actually don't have to understand this, but some of you are going on in science, and it's beneficial to have at least had your memory refreshed about vectors. So if we're measuring or start adding vector A and vector B, this is a 2-dimensional system, and so it's not as straightforward. What you do is you draw a parallelogram. So you draw a line parallel to vector B and a line parallel to vector A. The sum of those 2 vectors is the vector going from the origin of both of them to the opposite corner of the parallelogram. Here's another example, this one going off in that direction, that one going off in that direction. This line here, we draw parallel to the A, and this draw parallel to the B. It's a parallelogram, 2 parallel sides. And the sum of the vectors is from corner to corner. What if you have 3 vectors? Well, you add 2 first, and then you add the third. And if you had 4, then you'd add the 4th. So in this example, we've got A and B again. We draw a parallelogram, and we find that A plus B is R. Now we're going to add R to C. So there's R, here's C. We draw another parallelogram, and that gives us the net vector for the sum of A, B, and C. A, B, and C are going kind of in opposite directions, and they're different sizes, and so it's a little hard to see exactly what's going to happen, but you can kind of predict that's not going to add up to 0, right? And this is how you would figure out exactly what it does add up to. Here we have 3 vectors. These happen to be in 2 dimensions, so that's nice. So there's A, B, and C, and they're all the same length. And they're going in opposite directions. So if we add, well, not opposite, but they're equally spaced. This is a trigonal planar arrangement. If we add A and B, we get vector R. Then adding R and C, that adds up to 0. So what's different between this, which had a net vector, and this one, which has a net vector of 0, is that this one's symmetrical. The vectors have the same length, and they're spread out equally in space, and so they add up to 0. This gives us some common cases of looking at molecule geometries and which ones are going to have a dipole moment and which ones are not. That's nice, but I like this better. So here's my shortcut to molecular polarity. This does not always work, but it usually works, and that's good enough. So the molecule will be nonpolar if both of these conditions are true. No lone pairs on the central atom, and all the atoms bonded to the central atom are the same, or they have the same electronegativity. In Chem 1A, we'll mostly just be dealing with, are they the same or are they different? The reason that this works is when you have lone pairs on the central atom, that messes up the symmetry. So now we don't have all of the vectors going in opposite directions. When we don't have all of the atoms bonded to that central atom being the same, then the lengths of the vectors are different, and we're going to end up with a dipole. So the molecule would be polar if either of these is not true. So we're just going to use my shortcut instead of that vector addition stuff. So determine if CF4 is polar. We still have to start with the Lewis structure because we need to know, are there any lone pairs on the central atom? So put carbon in the middle and put the 4 fluorines around it and count up the electrons. Handing out electrons, everybody's got an octet. Check the formal charges, they're all 0, it's all good. Once we have that, now we can decide if it's polar or not. Are there any lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? Yeah. This is a nonpolar molecule. Oops. If we draw a picture of this, it's a tetrahedron, right? So we have 4, these are all polar bonds, right? Fluorine is more electronegative, and so these polar bonds are going out. Here's carbon in the middle, and the fluorines are spaced equally around it. If there was a lone pair, then the atoms wouldn't be spaced equally. But we have vectors going in opposite directions, and so you add them together, they'll all add up to 0. Any questions? So symmetry is a big deal for molecular polarity. If the molecule is not symmetrical, there's a good chance it's polar. Polarity is important because it has a big effect on the properties of the molecules. So polar and nonpolar molecules have very different properties. We know that oil and water don't mix together, right? And the polarity of the molecules is the reason. Oil is nonpolar, water is polar. For polar molecules, like water, the hydrogen end here is slightly positive, the negative end is slightly negative. There's a force of attraction between those partial charges. It's weak, but it is there. And so water molecules are attracted to each other. In a nonpolar molecule, like oil, there are some different types of attractions, but they are much weaker than this attraction between the water molecules. And so what effectively happens is like this picture. I need to get some of these marbles. These are magnetic marbles, the solid ones. And you all know what those would do. They're going to stick together, right? And these are just regular glass marbles. And you can try to mix all these up, but the magnetic marbles are strongly attracted to each other, and they're just going to squeeze out the glass marbles, right? That's what water does to nonpolar substances like oil. The water molecules are very attracted to each other because of those partial charges due to the polarity. So the water molecules just squeeze together and they exclude the nonpolar molecules. The reason that the oil floats is because it's less dense than water. There are other substances that are nonpolar that are more dense than water, and so they'll form a layer on the bottom of the beaker. Any questions? So let's talk about how soap works. You probably know from experience that if you've got butter or grease, Crisco, motor oil on your hands, you can't just rinse it off with water. It's not going to happen. The reason is that the water's polar and that the grease is nonpolar, and they're not going to mix together. The water just won't let it in. So we use soap. This is an illustration of a soap molecule. So a soap molecule has this long nonpolar tail. These are carbon-hydrogen bonds, which we should remember. Carbon-hydrogen bonds are nonpolar. So no matter what shape this part is, it's going to be nonpolar. At this end, we have a couple of oxygen atoms in there. So now we have oxygen-carbon bond, which is polar, and this is not symmetrical down here, and so this end is polar, and this long tail is nonpolar. So the polar end can mix in with the water just fine, and the nonpolar tail can mix with the grease. And so what happens, we've got a clump of grease, and, well, let's just use blue. The nonpolar tails of the soap can be inside the grease, but the polar heads of the soap molecules will not be in the grease. They'll be sticking on the outside. So you end up with all these polar heads on the outside of this little glob of grease. And so the water just sees the outside of that globule, and it's polar, and so it can get in among the water. So what soap does is it breaks the grease into small little micelles and surrounds them with polar heads so that they can escape. Any questions?